Alright, so in this video we're going to talk about these things called Fischer projections. Alright, and what these are ways of representing sugars or carbohydrates that take all the hassle out of drawing stereo sensors. Now, carbohydrates can exist in one of two forms. The cyclic form, this is the cyclic form of D-glucose, by the way, and later on we'll see exactly what that D means. This is the open chain form. In other words, this can cyclize to form this. This is of D-glucose as well. Now, as you can imagine, drawing this out with all these stereo sensors, if you have to draw that out several times, it gets to be kind of a pain in the butt. And so there is a way to actually make drawing this out easier, and that's drawing out like this, where the stereo sensors are not shown but they're implied. And these straight lines, this long line is the carbon 1 through 6 backbone, which is this guy here, and then each of the intersections is a carbon atom. They're always shown 1 to 6 pointing straight down with the dominant functional group at the top, and it's always a CH2OH at the bottom, always. So the only thing that differs is where the H and OH are on each carbon going down the middle. One thing about sugars is there is always an OH on every carbon in the middle, so the only thing you have to worry about is where the H and OH goes. Now, this does take some time getting used to, and the main thing we want to understand is, what does a Fischer projection actually mean? So what I'm going to do first off is we're going to take some time and go from a normal representation to a Fischer projection, so you guys can see what it actually means. So we're going to start here, and I'm going to show you how we can take this and convert it into a Fischer projection. Okay, now this is a Fischer projection of a big molecule with 6 carbons. We're going to do one with just one central carbon and then grow from there. So first off, I want you to convince yourselves that you can see that this actually does have the R stereochemistry. Priority 1, priority 2, priority 3. The hydrogen's already pointing away from us, so that is indeed R. What I want you guys to do, and this is one of the things that takes a little bit of practice and getting used to, is we're going to draw this out in a slightly different way. We're going to draw this out to show there are dashes going top and bottom. Now, these are supposed to be a straight line. I'm doing the best I can. And then coming out left and right are wedges. Alright, so here are our wedges. Now, how are we going to go from here to here? What I want you to imagine you're doing is you're positioning your eye here. There is your eye. And you're looking at that carbon in between the H and OH. The H is pointing back, so from your viewpoint it's pointing off to the left, but it's coming out towards you a little bit. And then the OH is coming out towards you, but it's pointing off to the right. And from the same point of view, the CHO aldehyde group, if you're looking at here, is pointing down like this, but it's up at the top. And then the CH2OH is on the other carbon looking like this. Alright. Now, this is one of the things that takes some time to get used to doing, being able to see this. So make sure that you can, and make sure that you can practice that. Because once you've done that, you just imagine that you're taking this molecule and you're going to take your hand and splat it flat right on top of this whole molecule. So you just go splat. So everything that was up becomes flat, everything that down becomes flat, and it gives you essentially a cross here, where all the groups stay in the same place they were before. And what we get is a Fischer projection. Okay. Okay, and that is exactly what a Fischer projection is. So the important thing is being able to go through this intermediate step. And the other thing that's really important to understand is the groups that are pointing on the cross, pointing at the top and the bottom, are the groups that are going into the page or on the dashes. The groups that are left and right are the groups that are really on wedges, so they're pointing out towards you. That's an important thing. The Fischer projection doesn't show it, but it implies it. Now we're going to talk about one more thing before we carry on. There's certain rotations you can do with Fischer projections that are allowed, certain that are not. Now this is still an R stereochemistry. So I want to show you rotations that we can do. You can take this and rotate it by 180 degrees. So I could take that whole thing and rotate it by 180 degrees. So I'm going to take that and do that rotation so my CH2OH ends up on the top. CH2OH ends up on the top. Therefore my CHO ends on the bottom. Alright. And my H ends up on the right, and my OH ends up on the left. Okay? So this is after a rotation of 180 degrees. The one thing you cannot do for a Fischer projection is rotate this molecule by 90 or 270 degrees. Because what that does is that alters the meaning of what the Fischer projection is representing. Now let me show you what I mean by that. I'm going to draw the same structure down here, but after 90 degree rotation. And let's say we're going to rotate 90 degrees to the right. So therefore my CHO is going to end up to the right here. And I'm just shifting everything one group to the right. Okay, so if we just do this, I'll put my hydrogen here, and then my CH2OH goes here. What I'm actually going to show you then is that this still equates to this R stereochemistry, this one does not. So we're actually going to go backwards from what we did before here. We went from here to here to here. Now we're going to go from here to here, back to here. So the first thing we do is we just draw this out in exactly the way we had it before. Alright, I'm going to do this. And I'm going to put these groups on top, CH2OH, and my hydrogen, and my OH, and my CHO. And this is the point where having models would be very, very helpful. You need to take this and rotate it so the two bonds coming out towards you are actually in the plane of the board, with the hydrogen going up and the OH going down to the left here. I'm going to draw on the wedge in the dash as well. Here's my wedge. Here's my dash. Now the question is, can you guys see which group goes where? I'm going to rotate this hydrogen up here so the OH stays in the plane of the board along with the hydrogen. That means the CH2OH, that should be a 2, is going away from us, and the CHO is going towards us. CHO is going towards us. Now, what that means is that stereochemistry is R. That's still the same stereochemistry as what we had before. But if I do the same thing here, and let's just do this, HOCH2, and this is actually on a wedge here, and I have on the other wedge my CHO, and then I have my hydrogen pointing like that and my OH pointing like this. If I do the same thing again and put the two groups that were these two groups here, but now that these groups here, my CHO pointing up like that. My CH2OH pointing like this. Well, that's me trying to do a dash there. My hydrogen here and my OH here. And hopefully what you can see is priority 1, priority 2, priority 3. This is no longer the R stereochemistry. So in other words, by doing this 90-degree rotation, we have changed the enantiomer of what we're looking at. Originally we had the R, now we have the S, and so that's why for 90 degrees and 270 degrees we can't do those rotations because they alter what we are looking at. So the only rotation we can do of the whole molecule is by 180 degrees. This is okay. Alright. Okay, that's a little bit about Fischer projections.